All right, hello. This is a video for how to use Statcrunch in Chapter 7 and Chapter 8. So these first few questions that I have over here on the left side are actually part of the Chapter 7 video. And I'm just going to go ahead and do the Statcrunch steps so you can see it. And then these last three are for Chapter 8. So it just has this different thing where we have a group rather than a single battery in this context. So I've got 12 batteries, 24 batteries, and 144 batteries. So this is just so we can see what that Chapter 8 sampling distributions looks like. All right, so to start with, of course, you need to be in Statcrunch. The easiest way to get there is if you're in the problem that you're working on, is just to go up to question help. And when you pull down question help, it should have Statcrunch as an option. Otherwise, you can also open Statcrunch directly from the left-hand menu when you're in My Labs Plus. I don't think I'm actually logged in. I'm logged into Statcrunch, but I think if I go to, try to come over here, well, there it is. So Statcrunch. There on the menu when you're on your My Labs Plus page. Okay. So we don't actually need to put any data in for the calculations. We're actually just going to use the calculator. And of course, we're doing a normal distribution calculator. So we're going to go to that. And this is what it should come up as when you just first open the calculator. And for the most part, we'll probably stick with standard. But there are a few times that we'll use the between. So between has the area between two numbers, as opposed to standard, which either has area to the left, or if we change this, area to the right. So I left part B, draw a graph of the probability distribution, so that we can see what that would look like if you're drawing it out on your paper. So to put it in here, we're just going to put our mean. So of course our mean is given to us 21.7 hours. And then our standard deviation is also given to us 1.2 hours. Now, if I go ahead and click compute, that's going to shade the entire graph because it's greater than or equal to 0. So 0, of course, is way, way down to the left of this point here. I like to, even though I don't necessarily use the empirical rule, I like to click this option here so that I can see, oh, yes, that's fine. So that I can see where the mean is, and then, the approximate 1 standard deviation away, 2 standard deviations away, and so on. If I do less than, I keep getting these errors, ignore those. Oh, well, okay. There we go. That's good enough. So this would be our graph with no shading. That is the graph of the probability distribution. We've got our normal curve. We've got our mean marked. Normally, what I would do if I was drawing this on paper, I would have one, ignore my fact that I'm not doing a very good job at just a straight line, but it's pretty close. I would have a straight line coming down to the mean, and then I would only really draw a line over and label the standard deviation. So I would have this number, and then I would say, 1.2. And that would be it if I were drawing this on paper. Of course, you don't have to show me your paper, so you can do whatever you want, but that's usually what I'll do if I'm answering any questions and I'm actually drawing them out on my app. Okay, so let me clear those out of the way. Okay, so next question. What proportion of AA batteries will last more than 24 hours? So more than 24, of course, it looks like it's going to be a little bit to the left of that 24.1, but it doesn't matter because all I have to do is come in here and I want to say greater than 24. And when I hit compute, it will shade that area for me. So greater than, more than 24 hours, and I get my answer. I'm going to go ahead and put it in here, type it in. simply because it might be nice for comparison's sake later. So 0.028. Oh, I did not make it bold like I wanted it to. There we go. So we can see that later. I might also make it red. It'll show up. Okay, so there, we already got that answer. If you've watched the video that I did, that's already posted before this, but that way we can look back in a minute. What percentage? So I changed this because they all said what proportion, but this you could have a question that says what percentage instead of what proportion. Same process. We're not doing anything different as far as using the normal distribution and finding area. In this case, though, we're looking for 21 hours or less. So that's going to be, right around in here, somewhere between 20.5 and 21.7. So somewhere in here, or less. So I'm going to go less than or equal to, but instead of 24, I'm going to change it to 21. And click compute. And there we go. So notice the shading matches up with what I am looking for. And so this is 0.2798. And so that's about 28%. So I might say, since that 8 would round the 9 to, actually, I guess the 79, that 2798. I don't really look if it's a 9. I think of it as a 2-digit number. So that 79 would get rounded to 80. So that actually turns out to be 28.0%. And I will also make that bold and red, just so we can see it later. Okay. So now we've gone greater than, or to the right. We've now done less than. Our next one is between. So I do need to switch over from standard to between. Notice it held my mean and standard deviation for me, but it's asking between -1 and 1. Well, that has no real meaning or context with this, because you can't have a negative time for a battery. And if a battery only lasted 1 hour, well, if the mean's 21, then of course that's 0. That's way down here again. If this graph were to continue, be way over here somewhere, and it's just a little tiny thing. So that's just the default. We can change that. In this case, we want it to be between 18 and 21. So 18 is our lower, 21 is our upper, and then we'll hit compute. And of course, 18 looks like it's going on forever, but it's really not. It's only going like to right here. And so if I did 17, it'd be a little bit different. And in fact, that really does get close to what we had, that 28%. But notice this is going to round to 0.279. So it's not quite the same. That's very close, though. I should have, if I would have seen that before I made the PowerPoint that I worked through, I probably would have changed those numbers a little bit. But that's okay. So what's the probability? Again, same idea, proportion, percentage, probability. They're all finding area. So what's the probability that a AA battery will last between 18 and 21 hours? Well, we're just going to do this to 3 decimal places. So 0.279. And bold red. There we go. All right. Oh, I made that so I didn't have to scroll. Put it back. There we go. All right. Next, we're wanting to find a value, not a probability. So we've got a battery company is considering a money-back guarantee for their batteries, but only want to have to risk giving a refund of 2%. So that basically means what value. So now we're going to try and do, whoops. We're going to put a value in here, and then it's going to, well, let's see, we don't want between. So let me go back. There we go. I'm sorry. We're going to put a value in this box to the right of the equal sign, and then we'll get an answer here. So we want to know what value, what time, battery life in hours, will we need for this refund to only be for the basically the bottom 2%. So that means that I want my area to be 0.02. And there we go. So that bottom 2%, they only want a refund if it doesn't last above this timeline or this time limit. And so if we want to go to maybe just one decimal place, we might say 19.2 hours. Okay. And so that's the bottom 2%. That's 2% of the batteries that they'll have to refund if someone has a problem with. But then we want to know for G, how long would the top 1% of batteries last? So same idea, but if I just change this to 1% and hit compute, look what happens. I'm still down here. I don't want that. That doesn't tell me what I'm really looking for. That's not the top 1%. This is like the best batteries that what are the best possibility? Well, this isn't it. That's the worst 1%. So I need to change this and then go back and make this 1%. When I compute, now I'm getting 24.5 hours. There we go. So that finishes up. That's what we've done in chapter 7 using Statcrunch. So hopefully that helps, along with the video that I posted where I talked a little bit more about what all these things meant and drew it out myself. Hopefully this kind of can tie in with that and help you see how to use Statcrunch. Now, in chapter 8, so this is all chapter 7 stuff. Wish I could just make it go away, but I can't. We're going to keep the same, so I'm just going to scroll up so that try to keep scrolling up. There we go. So that we just see these 3 questions. So these 3 questions are based on what we learned in chapter 8. And in chapter 8, we have a sample and our sampling distribution. And in this case, since we already knew that it was approximately normal, we were given that information to begin with, then our sample size doesn't matter. If it was not approximately normal, remember, we would need a larger sample size. But in this case, we've got a pack of 12 batteries and n equals 12 is fine. Now, the calculator doesn't give us a place to put sample size. Instead, we just need to adjust the standard deviation. So if a pack of 12 batteries is purchased, what's the chance that the mean battery life is more than 22 hours? So my mean stays the same. Mean of the sampling distribution is the mean of the population, so that does not change. The standard deviation of the sampling distribution is the standard deviation divided by the square root, and you literally can just type out SQRT, set of parentheses, and in this case, the sample size is 12, so square root of the sample size. Now, I do want greater than, and before we do 22, I want to do 24 just so we can compare. Just a sample of 12 versus 1. Notice this right here. And then let's compare that to what we had. So our probability was pretty small to start with when we had just 1. It was 0.028, or about 3%. This is 0.000000000, 10 zeros, and then a 152734. So that's extremely small number. If I wanted to write it out up here, let me see if I can. So 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. So I can't even fit it in a normal. There we go. That's that probability. That's what this number right here means. E to the negative 11. That is scientific notation. That E is not like the E on your calculator. It is just the way they're writing out. It means this number times 10 to the negative 11th power. And that means we move this decimal place back 11 places. So the first move gets us on the other side of the 1, and then the rest of them will be filled in with zeros. So 10 zeros, and then the number we have. All right, so that was just so we could see the comparison between 1 versus 12. And of course, the bigger our sample size gets, the smaller that number gets. But we don't want to know, we want to know more than 22 hours. And that's just slightly more than average, right? Average is 21.7. And again, I like to click this just so I can see the actual mean sitting there at in the middle, and then what these standard deviations. So this is a little more than just the last two standard, or it's not just this 2 standard deviations and more. One standard deviation and more. It is a little bit to the left of that. And so my probability though is 19 or 0.193. I was going to do it in percentage, but we'll stay consistent with what we've been doing for probability, and that's a decimal to 3 places. So there we go. There's our answer. Now, if let's compare. So that other one, this is kind of hard to compare because it's such a tiny bit. Let's take that square root off and see what would it be to just have one battery last more than 22 hours. So if we remove that and compute, notice that's much closer to half of the graph. So that as our standard deviation gets, or excuse me, as our sample size gets bigger, these standard deviations, because we're dividing by a bigger and bigger number, my standard deviation gets smaller, or my standard error, technically, standard deviation of the sampling distribution. And so these are less spread out, so it's less likely to have data over here in the tail. All right. Next up says if a pack of 24 batteries is purchased, what is the chance that the mean battery life is 21 hours or less? All right, so again, now we're going to change, and we're going to say square root of 24. And we want to change our symbol to less than, and we need to change our value to 21. Then we can compute. Now, there's that teensy tiny way over here. And I'm just going to, there we go. So just this little bitty bit here in the tail. It's a very small chance. And again, if we compare that with what we got earlier, because this one is the same. 0.002. Since we're going to 3 decimal places, of course that keeps going. But if we compare that to what we got in part D, that was 28% or 0.280. So much, much smaller probability there. All right, and then we have a case of 144 batteries. So 144, that's what we call that a gross. It is a dozen, or 12 squared. So when we take the square root, really we could just say divided by 12, but I'm going to just, for consistency, I'm just going to leave the square root there and say 144, because it's rare. If we do happen to get a nice number that's a perfect square, fine, you can divide by 12, or you can divide by, if it's a sample size of 100, divide by 10. Or you can just, for consistency's sake, I just, square root of whatever the number is. It doesn't matter. That way I don't end up dividing by the sample size by accident. I always remember that it's the square root of a number. And now I want between. So again, I need to go from standard to between. And it did keep my 144 there. But I need to change this because right now, if I tried to say between 18 and 21, that's over here somewhere, right? 18 is to the left of the very farthest, and 21, that's off our graph too. So that's over here somewhere. So that's a very, very, very small chance of having that value. So I had to change the problem up a little bit. And I said between 21.85 and 21.95, just so we could have something to check. Because otherwise, of course, when we divide 1.2 by 12, we're going to get 0.1. So notice that this is a very nice standard deviation or standard error of 0.1, 0.1, 0.1, minus 0.1, minus 0.1, minus 0.1. So that's why these numbers are so nice. And so 21.85 as our lower and 21.95 as our upper. And we see that's this area over here. And we've got about 0.061 if we round that to 3 decimal places. And so hopefully that helps both with understanding what we're doing with Chapter 8 and then also how to use the normal calculator.